Today we will discuss three-phase induction motor. So after completion of this session, the learners will be able to principle and working of three-phase induction motor and understand torque equation and slip of three-phase induction motor and torque slip characteristics of three-phase induction motor. So actually the three-phase induction motor works on the principle of Faraday's laws of electromagnetic induction, that is mutual induction. So mutual induction means, for example, there is, let us consider two coils, coil A and coil B, and when coil A is excited by the AC supply, an alternating current is circulating in the coil A itself. Due to that alternating current, the flux is produced in the coil A. According to Faraday's laws of electromagnetic induction, an EMF is induced in the coil A. That induced EMF is called self-induced EMF. And the flux produced in the coil A is cut by the neighboring coil B. So this is coil B. The flux produced in the coil A is cut by the neighboring coil B. So according to Faraday's laws of electromagnetic induction, an EMF is induced in the coil B itself. That induced EMF is called mutual induced EMF, and that phenomenon is called mutual induction. So the three-phase induction motor works on the principle of Faraday's laws of electromagnetic induction, that is mutual induction. The transformer, single-phase transformer, is also works on the principle of mutual induction, and as same as three-phase induction motor is also works on the principle of mutual induction. So both the machines works on the principle of mutual induction. Both the machines are works on the principle of mutual induction, but the single-phase transformer, the transformer is a static device, and three-phase induction motor is a rotating device. So that's why the three-phase induction motor is also called as rotating transformer. So both the machines, the transformer as well as three-phase induction motor, both the machines are works on the principle of Faraday's laws of electromagnetic induction, that is mutual induction. But transformer is a static device and three-phase induction motor is a rotating device. So that's why the three-phase induction motor is also called as rotating transformer. Okay. So when the three-phase supply is given to the stator three-phase winding, a rotating magnetic field is produced in the stator three-phase winding, and that rotating magnetic field is rotating with constant magnitude. Okay. When the three-phase supply is given to the stator three-phase winding, that in a rotating magnetic field is produced in the stator three-phase winding, and that rotating magnetic field is rotating with synchronous speed. Coming to this is the three-phase induction motor. So coming to the working of three-phase induction motor. Coming to the working of three-phase induction motor. So let us assume the direction of the rotating magnetic field is clockwise direction. The direction of the rotating magnetic field is clockwise direction. So observe my cursor. So the direction of the rotating magnetic field is clockwise direction. And when the three-phase supply is given to the stator three-phase winding, there exists a definite number of poles. So we consider only south pole. So this is the only south pole. Okay. So this is the only south pole. So we already know that the flux is always flows from north to south. So the flux lines is towards the south direction. Okay. So this is the rotor. So rotor has more number of conductors. The rotor has more number of conductors. So according to Faraday's laws of electromagnetic induction, that is mutual induction, the rotors are cut by this rotating magnetic field, and EMF is induced in the rotor conductors. That induced EMF is called mutual induced EMF. And in three-phase induction motor, the rotor conductors is already short circuited. So when EMF is induced in the rotor conductors, it circulates the currents. Okay, it circulates the currents. So let us consider only one conductor. So this is only one rotor conductor. We have more number of conductors, but we consider only one conductor. Okay. So the current direction is in this conductor is downward direction. So for example, the current direction in the conductor is downward direction. We indicate the cross. So for example, the current direction is upward direction. We indicate the dot. So here we indicate the cross. So therefore, the current flowing in this conductor is downward direction, and the rotating magnetic field direction is upward direction towards south. And the rotating magnetic field, the direction of the rotating magnetic field is clockwise direction, and the current flowing in the conductor is downward direction. Okay. So when current flowing in the conductor, when a current is flowing in the conductor, there exists a flux. So how to find the direction of the flux due to induced rotor current? How to find the flux direction of the flux? That is right hand thumb rule. So that is the Maxwell's right hand thumb rule. So the thumb indicates the direction of the current and fingers indicates the magnetic field. The thumb indicates the direction of current and fingers indicates the magnetic field. So in this diagram, the current is flowing in downward direction. So the flux is clockwise direction. The direction of the flux is clockwise direction. The flux due to induced rotor current is clockwise direction. So once observe the right side of the conductor, both the fluxes, that is rotating magnetic field and flux due to rotor current, these two fluxes are in opposite direction. These two fluxes are in opposite direction. So the flux lines is gradually decreasing. The flux lines is decreasing. Once observe the conductor left hand side, both the fluxes, that is the rotating magnetic field and the flux due to the rotor current, both the fluxes are in same direction. So the flux lines is increasing. So conductor right hand side, the right hand side of the conductor is flux lines is decreasing and more flux lines in the conductor left hand side. So the conductor is always moves from high flux density to low flux density. The conductor is always moves from high flux density to low flux density. So the conductor moves left to right. So the conductor, the direction of the rotation of the conductor is as same as the rotating magnetic field direction. Okay, the direction of the rotor conductor is the rotating magnetic field direction. Let us assume the rotating magnetic field is also clockwise direction and the direction of the conductor is also moving clockwise direction. Okay. So initially the rotor conductor is stationary and the rotating magnetic field is rotating with synchronous speed. So there exists a relative motion between the rotating magnetic field and rotor conductors. So for the motoring action in three-phase induction motor, for the motoring action, the relative motion between the rotating magnetic field and rotor conductors is very, very essential. This thing is very, very essential for the motoring action in three-phase induction motor. Okay. So due to interaction of two fluxes, the left of the rotor conductor and two fluxes are in the same direction, add up and get the high flux area. So the conductor is always moves from high flux density area to the low flux density area. So the rotor conductor always moves towards high flux area from the low flux area. So due to interaction of these two fluxes, the rotor conductor experiences a force from left to right in this case. So all the conductors experience a force. All the rotor conductors experience a force. The overall rotor conductors experience a torque and starts rotating. Okay. So the interaction of these two fluxes is very, very essential for motoring action. The interaction of these two fluxes, that means rotating magnetic field and flux due to rotor conductor. Flux due to rotor current flowing in the rotor conductor. These two fluxes, the interaction of these two fluxes is very, very essential for motoring action. So here Ns is the synchronous speed. That is the rotating magnetic field is rotating with synchronous speed. Synchronous speed means synchronous speed, rotating magnetic field in RPM. And where N is the speed in actual motor, speed of the rotor, that is the motor in RPM. So Ns minus N, the relative speed between the two rotating magnetic field and the rotor conductors. That is, it is also called as slip speed. So slip speed equal to difference between the synchronous speed and actual motor speed is also called as slip speed. That is the relative motion between the relative speed between the rotating magnetic field and rotor conductors. So this is also called as slip speed. Slip speed is also defined as the difference between the synchronous speed and rotor speed is called slip speed. Okay. Thus rotor always rotates in the same direction as that of rotating magnetic field. Okay. So next, torque equation. So actually the torque is defined as the turning or twisting moment of a force about an axis is called torque. The turning or twisting moment of a force about an axis is called torque. So in three-phase induction motor, the torque is mainly depends on rotating magnetic field, that is flux produced in the stator, and the rotor current in running condition, that is I2R, and the power factor of the rotor circuit in running condition, that is cos pi 2R. So therefore T is directly proportional to pi I2R cos pi 2R. Okay, the torque is directly proportional to pi. Pi means rotating magnetic field in the stator and I2R is the rotor current in running condition, and cos pi 2R is the power factor in rotor circuit in running condition. So T is directly proportional to pi I2R cos pi 2R. So we already know that pi is directly proportional to E1. E1 is the stator induced EMF, and E1 and E2 are related with the transformation ratio, that is E2 by E1 equal to K, where K is the transformation ratio, K equal to E2 by E1. So by using these two relations, I write the equation E2 is directly proportional to pi. Okay, so we already know that pi is directly proportional to E1, and we already know that transformation ratio K equal to E2 by E1. So by using these two relations, I write the equation E2 is directly proportional to pi. So in torque equation, that is T is directly proportional to pi I2R cos pi 2R. So in this equation, I replace the pi with E2. Okay. So and also I2R. So I2R equal to rotor current in running condition. That is I2R equal to E2R by Z2R. The formula is E2R by Z2R. That is E2R means rotor current in running condition, so rotor induced EMF in running condition, and Z2R is the rotor impedance in the running condition. So E2R equal to SE2. These are the rotor parameters affected by the slip. That is SE2, and Z2R equal to root of R2 square plus SX2 whole square. And also we already know that cos pi 2R. So cos pi 2R is the rotor power factor in the running condition. Cos pi 2R equal to R2 by Z2. R2 by Z2. So we already know that Z2R equal to R2 square plus SX2 whole square. So cos pi 2R equal to R2 by Z2R. So R2 by root of R2 square plus SX2 whole square. So substitute in these three equations in the torque equation. So T is directly proportional to pi is directly proportional to E2. So therefore E2 into I2R. I2R means SE2 divided by root of R2 square plus SX2 whole square, and cos pi 2R equal to R2 by root of R2 square plus SX2 whole square. So therefore T is directly proportional to SE2 square R2 by SE2 square R2 by R2 square plus SX2 whole square. SX2 whole square. T is directly proportional to SE2 square R2 by R2 square plus SX2 whole square. And also T equal to K into K means the proportionality constant. K into SE2 square R2 by R2 square plus SX2 whole square. So where K is the proportionality constant, so K equal to 3 by 2 pi ns, where ns is the synchronous speed in RPS, where ns is the synchronous speed in RPS, revolutions per second, and this equal to ns, that is synchronous speed in RPM by 60. Okay, so T equal to K into SE2 square R2 by R2 square plus SX2 whole square. So at the time of starting, n equal to 0 and s equal to 1. That means s equal to, we already know that ns minus n by ns. So put the n equal to 0 in this equation. So s equal to ns by n. So s equal to 1. So at the time of starting, n equal to 0, the rotor speed is 0 and slip equal to 1. So when n equal to ns, that is synchronous speed equal to rotor speed, this is not possible for three-phase induction motor. Why? Because, for example, when the three-phase supply is given to the stator three-phase winding, the rotor tries to rotate the synchronous speed and not rotate with synchronous speed. Okay, so when the three-phase supply is given to the stator three-phase winding, the rotor tries to rotate with synchronous speed. The rotating magnetic field is rotating with synchronous speed, but the rotor tries to rotate with synchronous speed, not rotate with synchronous speed. For example, if the rotor is also rotate with synchronous speed, that is n equal to ns, there is no relative motion between the rotating magnetic field and rotor conductor. So obviously the rotor comes to rest position. Okay, so n equal to ns, that is s equal to 0. This is not possible for three-phase induction motor. This is not possible for three-phase induction motor. Why? Because if the rotor is also rotated with synchronous speed, there is no relative motion between the relative speed or relative motion between the rotating magnetic field and rotor conductor. Obviously, the three-phase induction motor comes to rest position. Okay, so this is not possible. N equal to ns and s equal to 0. This is not possible for three-phase induction motor. Okay, so at the time of starting, s equal to 1. So put the s equal to 1 in this equation, then T is directly proportional to E2 square R2 by R2 square plus X2 square only. Okay, so in running condition, T is directly proportional to SE2 square R2 by R2 square plus SX2 whole square. That means the torque is ultimately depends on slip here. Okay, the torque is ultimately depends on slip. At the time of starting, slip S equal to 1. At the time of starting, slip S equal to 1. So therefore, T is directly proportional to E2 square R2 by R2 square plus X2 square. So that means at the time of starting, the rotor resistance, the torque is depends on the rotor resistance. Okay, so in case of squirrel cage rotor, in case of we are using squirrel cage rotor, the rotor resistance is very, very low. So for squirrel cage rotor, the torque is very, very low. It has low starting torque. In case of slip ring rotor, squirrel cage rotor, there is no insert the external resistance. There is no possibility to insert the external resistance while we are using squirrel cage rotor. So for squirrel cage rotor, the starting torque is very, very low. In case of slip ring rotor, there is a possibility to insert the external resistance by using the external rheostat through the slip rings and brushes. So by using, for example, in case of we are using slip ring rotor, we obtain the high starting torque. Okay. For example, we are using squirrel cage rotor, we obtain the low starting torque. So for example, we are using slip ring rotor, we obtain the high starting torque. So torque equation, so T is directly proportional to SE2 square R2 by R2 square plus SX2 whole square. Okay, T equal to 3 by 2 pi ns, where ns is the synchronous speed in RPS. So ns equal to synchronous speed in RPM by 60. So slip of induction motor. So slip is defined as the, first of all, slip speed. So slip speed is defined as the difference between synchronous speed and rotor actual motor speed is called slip speed. That is slip speed equal to ns minus n. So slip is defined as the difference between synchronous speed and actual motor speed, and it is expressed as a fraction of the synchronous speed is called slip speed, and it is denoted as S. So S equal to, we already know that S equal to ns minus n by ns. The percentage slip equal to ns minus n by ns into 100. So for the rotor speed, n equal to ns into 1 minus s. At the time of starting, we already know that at the time of starting, n is 0, n equal to 0. So therefore slip equal to 1. So slip S equal to 0 and n equal to ns is not possible for not possible for three-phase induction motor. Why? Because if the rotor is also rotated with synchronous speed, there is no relative motion between the rotating magnetic field and rotor conductor. So obviously the motor comes to rest position. So n equal to 0 and so n equal to ns and s equal to 0. This is not possible for three-phase induction motor. Okay. So at the time of starting, n equal to 0 and s equal to 1. So the torque is ultimately depends on slip. Okay. So coming to the torque slip characteristics. So the curve obtained by plotting torque against slip from s equal to 1 to s equal to 0 is called torque slip characteristics. So we already know that torque ultimately depends on slip, right? So the curve obtained by plotting torque against slip from s equal to 1 to s equal to 0 is called torque slip characteristics. For example, in case of three-phase induction motor, so the three-phase supply is given to the stator three-phase winding. The rotor tries to rotate the synchronous speed, not rotate with the synchronous speed. We already know that. So when the three-phase supply is given to the stator three-phase winding, the rotor tries to rotate with synchronous speed, not rotate with synchronous speed. For example, if the three-phase induction motor is loaded from no load to full load, when we apply the load on the transformer, then its speed is decreases. When its speed decreases, slip will be increases. According to formula S equal to ns minus n by ns, when the speed is decreases, slip will be increases. When the slip is increases, according to torque equation, torque must be increases. So to satisfy the load demand, torque is also increases to satisfy the load demand. Okay. So the torque equation, we already know that the torque equation T directly proportional to SE2 square R2 by R2 square plus SX2 square. For explaining the torque slip characteristics, so we apply the constant supply voltage. So therefore the E2, that is rotor induced EMF, is also constant. So the torque equation is rewritten as T is directly proportional to SR2 by R2 square plus SX2 whole square. Okay. So we apply the constant supply voltage. So therefore the induced EMF in the rotor is also constant. That is E2. It is denoted as E2. E2 is also constant. So therefore this torque equation is rewritten as T is directly proportional to SR2 by R2 square plus SX2 whole square. Okay. So for explaining the torque slip characteristics, the slip region, that is S equal to 1 to S equal to 0 to S equal to 1, the slip region can be divided into two parts. One is low slip region and second one is high slip region. Okay. For explaining the torque slip characteristics, the slip region, that is S equal to 0 to S equal to 1, the slip region can be divided into two parts. One is low slip region and another one is high slip region. So in low slip region, the name itself, low slip, the slip is very, very low. In low slip region, the slip is very, very low. So in the denominator, in the equation S is directly proportional to SR2 by R2 square plus SX2 square, the term SX2 square is very, very low as compared to the R2 square. Why? Because in low slip region, the slip is very, very low. The slip is very, very low. So due to that, the term SX2 whole square is very, very low as compared to the R2 square. So the term SX2 whole square is neglected in this torque equation. So therefore, T is directly proportional to SR2 by R2 square. So we already know that rotor resistance and reactance, these are also constant. Rotor resistance is also constant. So T is directly proportional to S. Okay. T is directly proportional to S. That means the torque is directly proportional to the slip. So we obtain the straight line. We obtain the straight line. That means the curve is linearly increasing. Okay, then we obtain the straight line. So that means when the load increases, load demand increases and the speed decreases. When the speed decreases, slip will be increases. When the slip is increases, torque is also increases according to the torque equation. The torque is also increases to satisfy the load demand. So T is directly proportional to S. When the slip increases, torque is also increases. T is directly proportional to S means. Okay. So in low slip region, so torque increases linearly in this region. Coming to the high slip region, next region is high slip region. So in low slip region, we obtain the straight line. So that means the three-phase induction motor can rotate continuously at any point in the low slip region. So that's why it is called stable region of operation. So coming to the high slip region, so the name itself, high slip region. In this region, the slip value is very, very high. So in the torque equation, the R2 square, that is rotor resistance, R2 square is very small as compared to the term SX2 whole square. Okay, the slip value is very, very high. So the term SX2 whole square is very, very high. So therefore, in the torque equation, the term R2 square is very, very small as compared to the SX2 square. So R2 square is neglecting the R2 square. So the equation is rewritten as T is directly proportional to SR2 by SX2 whole square. Okay, we neglect the R2 square in the denominator. So T is the equation, torque equation is rewritten as T is directly proportional to SR2 by SX2 whole square. Okay, T is directly proportional to SR2 by SX2 whole square. As we already know that R2 and X2 are constant. So therefore, T is directly proportional to 1 by S. Torque is directly proportional to the 1 by slip. That means torque is inversely proportional to the slip. Okay. So in low slip region, we obtain the torque is directly proportional to slip. But in high slip region, we obtain the torque is inversely proportional to slip. That means when the load increases, load demand increases, When the load increases, the speed will be decreases. When the speed decreases, slip will be increases. But according to this formula, T is directly proportional to S. When slip increases, torque must be decreases. But torque will be decreases. But torque must increase to satisfy the load demand, actually. Okay, you understand? So first, actually, when the load increases, load demand increases. When the load demand increases, speed will be decreases. When load increases, speed will be decreases. When speed decreases, slip increases. Okay, so according to this formula, T is directly proportional to N 1 by S. When slip increases, torque will be decreases, but torque must increase to satisfy the load demand. Torque must be increased to satisfy the load demand. Okay, but we increase the further load. We increase the load further, then the speed will be further decreases and the torque will be further decreases. Okay, so the induction motor comes to rest position in high slip region. That means in high slip region, we obtain the, according to T is directly proportional to S, that means we obtain the rectangular hyperbola. We obtain the rectangular hyperbola. That means the curve is like this. The curve is like this. So this is the low slip region. This is the high slip region. That means in three-phase induction motor, the three-phase induction motor cannot continue to rotate at any point in the high slip region. Okay, the three-phase induction motor cannot continue to rotate at any point in the high slip region. So that's why the high slip region is also called as unstable region of operation. The low slip region is called stable region of operation, and high slip region is also called as unstable region of operation. So this is the maximum slip. Sorry, this is the maximum torque. This is the maximum torque occur at maximum slip. Maximum torque occur at maximum slip. So maximum torque equal to K E2 square by 2x2. The condition, the maximum torque, the condition for maximum torque is S equal to SM. SM equal to R2 by X2. Okay. So the maximum torque occur at maximum slip. So this is the maximum slip. The maximum torque occur at maximum slip. The maximum torque equal to K E2 square by 2x2. Okay. So this is the high slip region, that is S equal to 0 to S equal to SM. So this is the low slip region, S equal to 0 to S equal to SM. This is the low slip region. So in this region, the three-phase induction motor, it can continue to rotate at any point in this region. So that's why this region is also called as a stable region of operation. Okay, and S equal to SM2 equal to S equal to 1. This is a high slip region. So the three-phase induction motor cannot continue to rotate at any point in this high slip region. So that's why this high slip region is also called as a stable region of operation. Okay, stable region of operation. So this is the maximum slip. Okay, we increase the, for example, we increase the resistance. This curve is like this. So the curve is also, the maximum torque is also up to this. So like this. Okay, so this is the torque slip characteristics. I think you are all understand what is the principle and working of three-phase induction motor, and what is torque and what is slip, and how to draw the torque slip characteristics. Okay, so thank you.